Is my screen visible to you?
Yes, sir.
Okay, please answer your attendance. Aditya Kumar,
Present, sir.
Anand,
Yes, sir.
Nanda Kumar,
Present, sir.
Arnachalam,
Yes, sir.
Hasan, Heyman,
Present, sir.
Jigan,
Yes, sir.
Kesav Prasad,
Yes, sir.
Lakshmi Narayanan,
Present, sir.
Prabhakaran,
Present, sir.
Prem Vinayak,
Present, sir.
Rahul,
Yes, sir.
Prajan Kumar,
Yes, sir.
Sabish Kumar,
Present, sir.
Satish Kumar,
Present, sir.
Titus,
Present, sir.
Valish,
Yes, sir.
Vigneshwaran,
Present, sir.
Vijayaraj,
Present, sir.
Vikash,
Present, sir.
Vivekanand,
Present, sir.
Yadav,
Yes, sir.
Yuvraj.
Present, sir.
Okay, the one who has not answered is Hasan.
Present, sir.
Hasan present?
No, sir. No.
Hasan is absent today. Okay. Okay, so welcome back. We are in chapter 3. Now we are discussing CI engine combustion. So I've given an overview of CI engine combustion. We discussed the different stages of combustion. We understood that in CI engine, the combustion takes place in 4 stages, starting with ignition delay, premix combustion phase, diffusion combustion phase, and afterburning phase. Among these 4 stages, ignition delay is an important stage. That's the first stage of combustion. Okay, based on the duration of ignition delay, the intensity of premix combustion is going to be different. And we know, based on the operating condition, the total fuel injected into the cylinder is constant. When you have a long delay, most of the fuel will be injected during delay, ignition delay time, so that the premix combustion, which is a subsequent phase of ignition delay, will result, there will be more intense premix combustion if there is a longer delay. If there is a shorter delay, premix will be of less intense. Because of that, you will have a more diffusion phase combustion. So overall combustion event in a CI engine is basically controlled by the delay time, which is the first stage of CI engine combustion. Okay, so that's the reason we bring out the various factors. One of the important factors is fuel-based factor, which is C10 number, measure of ignition quality that affects the ignition delay time, and also we discuss several engine design variables like, for example, compression ratio, and also operating variables like engine load, how it affects the ignition delay time. So ignition delay is an important stage of CI engine combustion. By properly controlling ignition delay, you can have a control over the combustion event, because the delay time is what is going to affect the subsequent phases of combustion like premix and diffusion phase. After this, we discuss about abnormal or knocking combustion in CI engine. It is primarily due to very long ignition delay. Very long ignition delay leads to more fuel being injected during the delay time, and that fuel injected during delay time will premix with air during that period of time, and then burns almost instantaneously during the second stage, which is premix or uncontrolled stage. When you have a longer ignition delay time, the quantity of fuel injected during delay is more, and because of that, the rate of pressure rise in the premix phase combustion is too high. And we discussed that above 8 bar per degree crank angle, the combustion is categorized as a knocking combustion. Pressurized rate will be very high. That is primarily due to more fuel injected during the ignition delay time. Okay, so the mechanism of abnormal combustion in CI engine is primarily governed by the duration of the delay. Longer the delay, there is a abnormal combustion, because locally you will have a very high pressurized rate during premix phase of combustion compared to the rest of the cylinder. Compared to average pressure, the local pressure is very high. This extreme pressure difference will result in violent gas vibrations and also pressure wave that strikes the cylinder wall, create this metallic ringing sound. It's audible to human ear. You can hear it. Decibel levels are high. Also, because of the waves hitting the cylinder wall, there will be vibration. Initially, the vibration will be felt in the cylinder wall domain, and then later on it will propagate to the crankshaft. So there will be vibration followed by combustion noise, high combustion noise. This is what is happening in knocking, same as what we discussed for SI engine, but here the mechanism is slightly different. We also discuss how this knocking event in CI engine is different from SI engine. Okay, what are the differences in the knocking event? Primarily, the important point there is knock in a CI engine happens during the initial stage of combustion because it is due to long delay, whereas knock in a SI engine happens during end of combustion because the knocking event happens due to self-ignition of N gas. So when I say N gas, it is a charge located far away from the spark plug. The flame during the termination stage or last stage only, it will reach the N gas. So knock in a SI engine happens near the end of combustion, whereas knock in a CI engine happens during start of combustion. Also, the intensity of knock will be very high in SI engine for two reasons. One, you have a homogeneous fuel air mixture. Second one, the operating fee is around stoichiometry or slightly rich, which will result in very high temperature in the cylinder. So engine operating temperatures are always high in SI engine compared to CI engine because CI engines are prone to lean combustion. You always have excess air. Operating temperatures are less in CI engine because of that. So the damage of knocking is severe in SI engine compared to CI engine because of this reason. Today, I'm going to discuss the last topic in this chapter, combustion chambers for CI engine. Already we discussed for SI engine. Now we are going to discuss about combustion chambers for CI engine. After that, I will discuss the questions that I have shared with you. I hope all of you have received my assignment questions. I will discuss about those questions briefly. The idea is I will give you the solution procedure, note down the solution procedure to answer those questions, and then you may have to submit it as an assignment. So combustion chambers for CI engine, one of the major consideration in SI engine, we have discussed that the combustion chamber design is based on three considerations. One is to get a high power output. Second one to get high thermal efficiency, and third one we want to have a smoother combustion without any knock. So all these are dependent on the combustion chamber design in SI engine. So we design, when I say that we design a combustion chamber, it involves location of the intake and exhaust valve, location of spark plug, also the shape of the cylinder head and piston. All this put together is the design aspect of combustion chamber. So in SI engine, we have three considerations: power output, thermal efficiency, avoiding knock. In CI engine, we have only one major consideration. We need to improve the rate of fuel air mixing. We have to design combustion chamber in such a way that it creates enhanced rate of fuel air mixing. So why mixing is important, so important in CI engine compared to SI engine? We already discussed about that.
Yeah, because you have told that if the mixing is not happening properly, if there is no motion around the flame, it might die. Because once the flame is like generated, so after the boundary is, if the boundary insulated actually in that way, then because of lack of oxygen, the flame will not propagate fast, and if there is no movement around the flame, so it might die. So hence the what I'm going to say, the fuel mixing is very important aspect of CI engine.
Yeah. So when you inject the fuel, right? So you have a spray profile. At the outer periphery of the spray, you have drops formation. Then air will enter in. Okay, mix with so once the air enter in, the liquid phase fuel will get into gas phase. Okay, then you have this P ignition. right? Once you have Phe ignition and T ignition, combustion is going to get started, okay, with the radical formation. So this generally happens around the periphery of the spray or boundary of the spray, the combustion gets started. If you don't have, and this is surrounded by air, if you don't have any air motion in the, suppose we assume that the combustion chamber is quiescent. Quiescent means without any air motion. Then what will happen? There will be ignition around the spray boundary. Since there is no air motion, the products of combustion, you know what are the products of major products of combustion. So you will have products of combustion located in this region around the spray boundary. Okay, since there is no air motion. So because of this, the access to air get stopped. So you have a core region, you have fuel drops or fuel films available here, and they don't have access to air. Because of this, this is called choked condition. Choked condition. Combustion gets started, but it cannot sustain. It cannot, whatever ignition happens is going to get stopped after some time because it is surrounded by its own product. Right. So what we expect is we want to create an air motion so that the products of combustion move away from this zone and air enters into the zone. So we want the fresh air to enter into the spray zone so that the entire fuel gets access to the air. Until otherwise this fuel get access to the air, it is not going to burn because it has to be raised to the ignition limit. Until otherwise this happens, there is no combustion of the injected fuel. So it's very important to create air motion in a CI engine. That's why CI engine combustion is also called mixing limited combustion. So you need to create the air motion in the cylinder. Otherwise, there is no combustion at all. The other important reason is the time available for mixing is very limited in a, it's very low in a CI engine. Why?
Because only air is injected. Where only air is injected in the combustion chamber.
Only air is taken into the combustion chamber during intake stroke. Fuel is sprayed during later part of compression stroke. Almost near the end of compression, you are introducing fuel. So the time for fuel or mixing is very limited because of this reason. Just now we discussed that after fuel injection, there is a delay time. We want to minimize the delay time. Otherwise, you end up in knocking combustion. So you introduce fuel very late during end of compression stroke, and with a very short delay time, combustion gets started. So it means the time available between start of fuel injection and start of combustion for mixing fuel and air is very low. It's very low. Okay. That's the reason why we end up in having heterogeneous combustion, heterogeneous mixture. We already discussed about that. So the mixing time is very limited. Okay, and if you don't create air motion, as I just now discussed, you're going to get a choked condition wherein the combustion even cannot progress further. It will get started, but it cannot progress. It cannot move ahead. So considering all this, we need to create appreciable air motion. Okay, so the major task in designing combustion chambers for CI engine is you have to enhance or improve the rate of fuel air mixing by providing sufficient air motion. And the sufficient air motion can be provided through combustion chamber design. So this is a major design criteria for CI engine. We have to design combustion chamber in such a way that you create appreciable air motion inside the cylinder. This is very, very important. Okay, and this is a primary criteria in designing the combustion chambers for CI engine, considering the limited mixing time we have. So how do we create air motion? We already discussed about that. It's just a recap of what we have discussed earlier to create air motion. Air motion can be created during the intake stroke, which is a circular motion or rotational motion called swirl. Swirl is rotational motion as we have discussed. So this is swirl, and this swirl, which is a rotational motion, can be created by shaping the intake manifold. Instead of a straight manifold, if you have a helical manifold, you're going to impart circular motion to the incoming air. So air enters with a circular motion into the engine cylinder. So this is what we call it as an intake swirl, and this is based on the design of the intake manifold. What is the limitation of this approach we discussed?
The volume efficiency comes down, sir.
Yes. volumetric efficiency is going to drop in this case because of high pressure drop. There is a high pressure drop with this kind of manifold design during the intake process. High pressure drop will result in less mass entering into the cylinder, so it will have an impact on the volumetric efficiency. When mass inducted is less, power output will get reduced. This is a limitation of having a helical manifold from the perspective of increasing air motion. Okay. One of the solution is you can go with something called intake valve masking. Intake valve masking is shown in the second schematic. So what is done here is in the intake valve, as you could see, there is a metal piece fixed around the circumference of the intake valve up to certain direction. Okay, so you could this is a sectional view, and you could see here that you have a circular metal piece fixed to the intake valve. When air enters, it is guided through the metal piece, and the incoming air undergoes a swirl, as you could see here. So we are creating a swirl or circular or rotational motion by having a metal piece fixed to the intake manifold. Although we are restricting the airflow here, the airflow is made to undergo a swirling motion because of having this metal piece. So this is a kind of creating swirl by masking a part or portion of the intake valve. That's why it is called intake valve masking. So we are creating air swirl during the intake stroke by having this additional attachment in the intake valve. Okay, and this avoids this pressure drop penalty whatever we encounter with a helical manifold, and that can be avoided by having this mask, but the intensity of the swirl will be relatively less here compared to the first case. We can also create swirl and squeeze during the compression stroke, as we have discussed, and this is based on the shape of the piston, shape of the cylinder head. So when the piston moves up during the compression stroke, okay, the charge contained in this region will be squeezed or compressed to go inward. So that's a motion we are generating, and this motion is called squeeze motion. The charge at the corners of the cylinders right here are forced to enter towards the center due to the piston upward motion. That's the piston upward motion forcing the charge from the corners to move towards the center. This is a radial motion or squeeze motion. When you have a flat piston, you will have only this squeeze. But instead of having a flat piston, if you have a bowl in the piston, this radial motion, once the charge from this end hits this corner, this is called piston lip. Once it hits this region, it undergoes a swirl. Similarly, the charge from this direction will hit here and undergoes a swirling motion. So we are creating a rotational motion from the radial motion. Both squeeze and swirl are generated based on the shape of the piston crown or piston top. Okay, anyway, piston upward motion is going to create squeeze. You can convert that squeeze into swirl by having proper shape in the piston top or piston crown. Okay, and this is done during compression stroke. This is preferable. This compression stroke based squeeze or swirl is preferable compared to the intake stroke based swirl, because you don't have any volumetric efficiency penalty here, because this is done after the induction of the air. Okay, and this is more preferable, and generally we go with this option to generate squeeze and swirl, appreciable air motion, so that the fuel air mixing is improved. So with this background information about the type of motions you can create by designing the intake manifold or valve or piston, we are now going into the types of the chambers, combustion chambers available for CI engine. Basically, the combustion chambers are of two categories. One is called open chamber. The other one is called divided chamber. In the open chamber, the entire combustion chamber is located in the main cylinder. Entire combustion chamber is located in the main cylinder. This is also called direct injection type diesel engine. The other one, divided chamber, is also called indirect injection type, IDI type engine, CI engine. This has become obsolete now. You don't see any IDI diesel engine running on road. Earlier, this type of design was used for passenger car. Diesel passenger cars are IDI type. Now we go with only open type chamber. I will tell the reason behind this. Before that, let us look into the features of this two design. As I said, in the open chamber, the entire combustion chamber is located in one region, that is in the main cylinder. So you have piston of different shape. So this is the main cylinder or main chamber. So you have only one combustion chamber here. Whereas in an IDI type or divided chamber type, you could see that there is a main chamber here as similar to the open type, but there is another chamber here in the cylinder head. So you could see that the head is connected with this chamber, it's called as auxiliary chamber, through a small throat. There is a small passage, like a nozzle-like passage that connects the main chamber and the auxiliary chamber. So you have part of the combustion chamber located in the main cylinder called main chamber. Another part of the combustion chamber is located in the cylinder head referred to as auxiliary chamber. Fuel injection happens only in the auxiliary chamber. Okay. Now let us look at how this works. When the piston moves up, it compresses the air. Okay. At the end of compression, the energy levels in the cylinder is so high because of very high compression effect. So air will rush into the auxiliary chamber through this throat. Throat is like a nozzle, very small flow area. What will happen because of this?
Velocity will increase.
Velocity will increase where?
In the auxiliary chamber actually, because
auxiliary chamber. So since you are forcing air with high energy through this throat, it's like a nozzle. Okay, you know what is the function of a nozzle? Pressure energy will be converted into kinetic energy. So the air will leave at very high velocity at the exit of the throat and then enters into the auxiliary chamber. In the auxiliary chamber, this incoming air is guided to undergo a swirl or rotational motion. Very high swirl will be generated. The swirl levels generated here are very high. So you cannot get such a high swirl in an open chamber. So here also you get swirl in an open chamber, but the swirl levels in a divided chamber is so high. It's almost 10 times. Swirl is characterized by something called swirl ratio. The swirl ratio in an IDI engine is almost 10 times higher. Okay, so this is 10 times higher compared to open chamber. Very high swirl is generated and the fuel is sprayed here. You have a high relative velocity between fuel and air in the auxiliary chamber. Mixing is so quick. There is an enhanced rate of mixing of fuel and air. So fuel will get into free ignitable range so quickly because of this reason. Okay, and then once if it is raised to its self-ignition temperature, combustion is going to get started. Combustion, where does it start? It starts in the auxiliary chamber. Ignition happens in the auxiliary chamber, combustion gets started. Once the combustion started, you know, pressure and temperature will shoot up in the auxiliary chamber. So from the auxiliary chamber, pressure and temperature will be very high compared to the main chamber. So there will be reverse flow. The mixture at high pressure and temperature will flow back into main chamber. Okay, and unburned fuel will also flow back into main chamber. Combustion will continue to happen in the main chamber. This is how this system work, IDI system work, wherein combustion gets initiated in the auxiliary chamber and then it continues to happen in the main chamber. And the swirl levels are so high, almost 10 times high compared to what you get in an open chamber. Okay, so just now I said that in CA engine, the time available for mixing is limited. And this time I can say that it is inversely proportional to engine running speed. When engine runs at very high RPM, the time available for mixing will be accordingly very low. So if you talk about a different category of diesel engine, passenger cars, you know, passenger cars run at high RPM compared to the other engines which are stationary or heavy engines. Okay, passenger cars generally run at high RPM. So engine running speed is very high. Mixing time is very limited. That's why IDA engines are used in passenger car applications earlier. Typical running speed is around 5,000 to 7,000. Okay, anywhere between 4,000 to 7,000. That's a typical running speed. mixing time is very limited. So they create a very high swell with this design, and that is how they are able to run at high RPM. Otherwise, you cannot even run the diesel engine at a high RPM until otherwise you create a ignitable mixture within the short time interval. Otherwise, there is no ignition at all. Okay, this is the advantage of having a divided chamber, but I inform you that this has become obsolete. There are no divided chamber or IDA engine. We go with only open chamber. Can you tell me the limitation of this design, divided chamber design?
Flame propagation constraints, something like that.
No. SI engine only has a flame propagation based combustion. CA engine, you will have ignition at multiple sites. Wherever you have P ignition and T ignition, ignition is going to happen. There is no one finite flame propagating.
Yeah, but within the divided chamber, we'll have a more richer mixture compared to the main chamber.
Sir, wall wetting phenomena may be dominant in this case because fuel will be injected in a smaller compartment and mixing will also be difficult. So
you mean to
that
say
may
that
be
the fuel may form a film around the boundaries, solid boundaries?
Yes.
And it takes more time for vaporization and mixing.
Yes.
Yes.
So in my opinion, it will be like basically the torque available for the this type of arrangement will be lesser compared to the like direct injection, because what is happening is we are burning the fuel air in the auxiliary chamber. There is a pressure rise happening over there, and then the flame propagates to the main chamber in that way. So basically, the some energy is lost in between during transition. So that will lead to lower peak pressure compared to the like direct injection. So probably the power output for the same CC of the engine will lesser compared to in this configuration compared to direct
Here
injection configuration.
the power output or torque output is primarily dependent on how much of fuel you are injecting, whether you are able to burn that fuel or not. Only these two simple consideration. Total fuel injected, out of total fuel, how much is burnt. If you burn all the fuel, you are going to get the required torque output. Okay. If you inject more and if you are able to burn all the fuel, you're going to get the required torque. There is more severe problem that you people are missing. There is a severe problem, the divided design.
The complete combustion is happening in the pre-chamber. So the designing pre-chamber has to be withstand, for example, 90 bar or 100 bar. So that will be critical.
Okay, so you're talking from a design consideration that the gradients, pressure and temperature are so high, there may be a durability problem, right?
Right.
NOx formation may be highest.
NOx will be high, okay.
Exactly.
What will be, so when I say that the passenger car, you don't have any IDA design, as an end user, what you will look at primarily? If you buy a passenger car, IDA type car,
Fuel consumption will be
fuel consumption. More specifically, mileage. So what will be mileage in IDA type engine? Will it be higher or lower?
Lower. Mileage will be lower.
Mileage will be lower.
Because losses will be more.
What losses?
Because you are direct, we are not getting complete forces to the piston on the main chamber, because unlike direct injection, because it is the combustion happening at the next chamber, auxiliary chamber, and then the energy transferred from the auxiliary chamber to main chamber.
Yeah, the major problem, this is a core problem. There is a poor mileage with IDA engine. IDA engine cannot be compared with the DA engine in terms of mileage. Mileage is very poor. Major reason for poor mileage is high heat loss. Heat loss in IDA engine is so high. Why it is so high? For two reasons. One, surface to volume ratio. You look at the auxiliary chamber, surface to volume ratio is high. So there is more surface available for heat loss. Surface to volume ratio is high, and due to very high swell, heat transfer coefficient is high. heat loss by convective mode, you know, it is HA delta T, surface area and H. This H is a function of velocity, fluid velocity. Okay, since you are generating very high swirl, H value is going to be high. Convective mode of heat transfer to the surrounding coolant. You are not insulated the auxiliary chamber, remember. Okay, so it is going to radiate heat. It is going to lose heat by convective mode, radiative mode, okay, to the nearby coolant. So this heat loss in IDA type engines are so high for two reasons. One, high surface available for heat transfer. Second one, heat transfer coefficient is high since the fluid velocity is so high in the auxiliary chamber. The coefficient, heat transfer coefficient is high. Okay, so there is a very high heat loss that directly reflects in very low thermal efficiency. Since you are not converting this heat into work, useful work. Okay, and thermal efficiency will be low, and mileage, this will directly reflect in the mileage. Mileage is going to be poor. This is the reason why IDA engines have become obsolete. To run engine at high RPM, okay, in passenger car application, you have to create a mixing, record mixing, FLR mixing within the very limited time because engine running speed is high. So in order to enhance the rate of mixing, you have created a very high swirl. But because of that, you get into another problem of high heat loss. High heat loss causes poor mileage. That's why these engines are discarded. There is no IDA type engine running on road, okay, based on this principle, primarily due to very poor mileage. In fact, you may have to use some starting aid like glow plug to start this engine, because at the time of starting also, since the heat loss is very high, you may not even be able to reach the self-ignition temperature. Okay, so you use some starting aids like glow plug in the IDA engine to start the engine. Okay, so heat loss is so high. To that level, you can imagine. You cannot even start the engine, especially under cold weather conditions. So this is a problem with these kind of engine. That's why they are discarded, and we go with only direct injection type. But you know, diesel engines are used in passenger car applications even today, and we are running at high RPM with direct injection type diesel engine. Then my question to you is how this problem is addressed. You are not going to get a high swirl, high air swirl as you get in a IDA engine. In a DA engine, the swirl levels are less. Then how do we create the record mixing with a limited time? Since
because of high injection pressure, sir.
Exactly, because of high injection pressure. So these IDA engines were introduced in the time wherein you have only mechanical fuel injection system. You know, in a mechanical fuel injection system, the injection pressure is limited 200 to 250 bar. The mixing, fuel air mixing is dependent on the relative velocity between fuel and air. You can increase relative velocity by increasing fuel velocity, air velocity, or both. Okay. Since you have a cap of 200 to 250 bar pressure, injection pressure, the velocity of the fuel is less. You know, fuel velocity is dependent on the fuel injection pressure. Since this is low, fuel velocity is low. That's why you are creating a very high swirl to run engine at high RPM. This is well taken in the current engine, because current engine we use electronic injection system. In an electronic injection system, you know how much is a fuel pressure, injection pressure?
Up to 3000 bar, sir, maximum.
Yeah, 3000 bar also you can reach. It's highly flexible. You can vary anywhere between 300 bar to 3000 bar. So you can inject at very high pressure. Since you are injecting at very high pressure, the fuel velocity is high. Although you have a less air velocity, less air swirl, injected fuel is at a higher pressure. Due to its higher pressure, it is at higher velocity. So you are creating better mixing, fuel air mixing, which is not possible if you have a mechanical system. So you have upper cap, due to which you are creating a very high swirl. This constraint is not there if you have a high pressure injection system. Although air swirl is less, fuel velocity is high, so mixing is better. So that is how we take care of mixing with the limited time we have in passenger car applications. That's why we are using this with a better mileage. Since the air swirl is low, considerably low compared to IDA engine, you have a better mileage in this type of engines. Clear? Now we are looking at possible combustion chamber designs. 4 different types of combustion chambers are shown here based on how we shape the piston. So in all these 4 designs, you could see that cylinder head is flat, but piston shape is different, right? You just observe the shape of the piston. In the first case, you have something like this. Here you have similar to letter omega. The shape of the piston is like this. Cylinder head is flat. Here, cylinder head is flat. Piston crown is shaped like this. This is hemispherical design. This is shallow ball design. Deep toroidal bowl and shallow toroidal bowl. In a shallow toroidal bowl also you have a divided cavity. This is called divided cavity, and the other one is single cavity. Okay, single cavity and divided cavity. So what difference? The cylinder head is flat, but piston top is of different shape to create air motion, which is our primary consideration in CI engine combustion chambers. Okay, you have to create air motion. What difference you have noticed with respect to air swirl in these 4 designs? What is changing here? So here you should notice 2 important dimensions. One is called width. So this is the width of the ball width, and other one is depth. Depth is from here to here. So this is depth of the ball. The other one is width. If you look at shallow ball, you have a higher width, you have a lesser depth. If you have a higher width and lesser depth, what will be the squish and swirl that you can generate, high or low?
Sir, squish will be high, right?
Squish will be high. Again, recollect what we have discussed about squish, which is a radial motion. It will be generated from this region. Okay, the charge contained in this region, in this 2 region, in the corners, will be subjected to squish. This is subjected to radial motion. From here, it will go towards the center. Do you think that the squish levels are high here in a shallow ball?
No, sir. I think the
No, sir.
obstruction
It will be lower. It will be lower, I think so.
It will be lower. Squish will be lower. Why it is lower?
Because
the amount of air being squished is low. Because of
basically the
that is the 4th thing you captured. The amount of air handled will be less here. The amount of air handled for squish motion is dependent on what?
top surface area.
This area. Can I say this area? Whatever highlighted in red color. This area is available. Whatever air contained in this area is undergoing the squeeze. If you have more area here, more volume here, there will be more air mass contained in this region. If you have a less region there, then accordingly the air mass contained in that region is less. If air mass is less, intensity of squeeze is going to be less. So in a shallow ball, so the air mass contained in this region is dependent on the width and depth ratio. Please note that this width to depth ratio will decide the clearance volume. So for a given compression ratio, clearance ratio is fixed. This is constant. And this constant value of clearance volume will be based on W as well as D. So you can have different values of W and D, still you can maintain a constant clearance volume. Did you get what I am saying? Compression ratio is constant. For a given compression ratio, VC is constant, but this constant VC can be achieved with any value of width and depth. Did you get what I am saying?
Yes, sir.
Yes, sir. Yes, sir. Yes, sir. Yes, sir.
So by adjusting W and D, you can maintain a constant VC, but what is happening here? The air motion is different based on width and depth. When width is more, depth is less, you are having less squeeze region. When squeeze region is less, intensity of squeeze will be less. Remember that during compression stroke, the squeeze is converted to swirl. Suppose if squeeze is less, swirl will also be less. Okay, because the swirling motion is a subsequent motion of squeeze. The air from the squeeze motion, it's undergoing a swirling or rotational motion in this region. Okay, so if the squeeze levels are less, then swirl will also be reduced. In a shallow ball, both squeeze and swirl are less because you have a larger width and you have a lesser depth. The squeeze region is reduced due to this, and there is a less intense squeeze that will translate into less intense swirl. Due to less squeeze and swirl, the air mixing is not better compared to the other design. So this is generally used in small, not small, low speed engine. So shallow ball is used in low speed diesel engine because of this reason. Can you tell me why it is used in low speed diesel engine?
Cost will be lower, sir.
Cost
And we
will-
don't need.
No, no,
we
from
don't
the
No,
first-
you will have more mixing times available actually.
Exactly. So here we are looking at everything from the perspective of mixing, fuel air mixing, because that is our consideration when we design the CI engine combustion chamber. In a low speed engine, you have more time available for mixing because engine is running at a very low RPM. Opposite to what we have discussed just now for IDA engine. IDA engines are designed to create the required mixing with a limited time since the engine is running at high RPM, passenger car. Okay. But when you run the engine at a low speed, the opposite effect, you have more time available for mixing. There is some flexibility here, and due to which we can even use shallow bowl. Also remember that when you have a less intense squeeze and swirl or less intense air motion in the cylinder, the heat loss from the engine cylinder is also accordingly reduced. We earlier discussed that very high turbulence will also cause a limitation of high heat loss, okay, because the air velocity is high and during combustion the gases are generated at high velocity that will increase the heat loss from the cylinder to the outside coolant. Now when you go back to the hemispherical design, you could see that the squeeze region is relatively increased. Did you observe this? Because you have relatively less width, you have more depth. So squeeze region is somewhat enhanced in this design, and this will translate into swirl. Of course, you can adjust, you can vary this W by D ratio. Okay, so you can have any depth for a given width, and accordingly you can maintain the given clearance volume. So compared to shallow bowl, hemispherical bowl creates somewhat higher squeeze, higher swirl, because you are having a more squeeze region, relatively more compared to the shallow bowl region. Now the bottom one, shallow toroidal and deep toroidal, the difference is in the top one, you have a hemispherical, if you look at, you have a single piston cavity. Here you have a dual kind of cavity, okay, or you can say the divided cavity. Piston cavity is divided. Here it is in the form of letter omega, is somewhat shallow, not in the form of omega. But here also you could see that the squeeze region is relatively less. So intensity of squeeze and swirl will be less, but you are having a more swirl region and you are having a divided cavity. So here you have a larger squeeze region. This will translate into swirl here. Here also it will get translated. So squeeze and swirl both are better in the deep toroidal design compared to the all other three designs. So you have a more squeeze region, create a very high intense squeeze, and you are also creating a high intense wall by having a divided kind of cavity. Okay, so this is the deep toroidal bowl design, which is primarily used in high speed diesel engines, wherein you have limited mixing time. High speed engines go with the deep toroidal design. Low speed engines, diesel engines, go with shallow bowl. So based on the engine running speed, you can fix the piston shape, and according to the width and depth of the cavity in the piston, you are actually changing the intensity of the squeeze as well as swirl. Okay, swirl can be more intense if you have a divided cavity. That is what is shown in the bottom row compared to the upward, the first row, wherein you have single cavity, especially in the hemispherical. So here there is no use of having this kind of design. Anyway, the squeeze intensity is very low, right? So you cannot create a high swirl in the shallow bowl. Okay, so based on the engine running speed, you can fix an appropriate design, piston design, that is going to create differences in the air motion, squeeze and swirl motion. Accordingly, the mixing rate of mixing is going to be different. Clear?
Clear, sir.
Audible.
Okay.
Sir, am I audible?
Yeah, audible.
Sir, can you just comment on the stress concentration aspects of these four different designs? Like at the edge of the piston crown, for the case of a shallow bowl, that concentration would be high, right? Stress concentration, because that area of flatland that is available is less than.
No, so you're talking about this area.
Yes, sir, exactly.
Okay, so what is your point here?
I felt that the
Thermal stresses.
that the edge would be subjected to more thermal stresses, and that is not preferable.
Yes, exactly. Because you also see that the surface here exposed to the hot combustion gases. I mean, the surface of the piston exposed to the hot combustion gases is high. So thermal stresses are going to be high with this shallow bowl design. Exactly. So thermal stresses will be high here compared to this design. The thermal stresses in the piston is based on how much of its surface is exposed to the hot combustion gases. Surface to volume ratio again will play a role. For two reasons. One, heat loss from the combustion chamber surface is exposed to hot combustion gases. So the piston has to be heavier in a shallow bowl design in order to withstand these thermal stresses. Generally, this problem is addressed by increasing the material for the piston.
Just a counterintuitive point, sir. For example, in deep toroidal, that edge seems to be a pointed V kind of a shape, right?
No, it's generally rounded. It is the schematic looks like this, but generally they don't have any sharp. You should not have any sharp corners here. That is also going to result in pressure drop.
Yeah. Got it, sir. Clear.
So you will have a rounded. You should have a rounded corners. You should not have a sharp corners.
Thank you, sir.
Okay. So now coming back to the questions, assignment questions that I have circulated to you, I will briefly go through the solution procedure for this questions. Note down the solution procedure and submit it as an assignment like you have done last time. And you have two assignments. This is the second one. You can take a week time. Maybe by next week, Wednesday, you can submit. Is that fine?
Coming Saturday, we have midsum, sir.
Okay.
Is it possible to do one more week?
So then we can, I will extend it to week after next.
Yes, sir. Thanks, sir. Thanks.
Coming Saturday, you have your midsum exam, right?
Yes. Vehicle time next.
Okay. So week after next on Monday?
Definitely, sir. We will do it.
Okay.
Week after next on Monday, not coming Wednesday. Week after next on Monday, you can submit this.
Sure, sir.
1st April.
1st April.
Yeah.
Sure, sir. We will do it, sir.
Okay.
Sir, for quiz 2 up to which syllabus, sir?
Quiz 2, whatever contents we discuss until the exam time, I will, all those you have to go through.
Okay, sir.
Probably chapter 3 and 4 you may have to go through, but I will see how much of chapter 4 will be covered. Chapter 3 is over now. Chapter 4 is a shorter chapter. So this 2 can be the syllabus for your quiz 2.
Okay, sir. Okay.
Your quiz 2 is fixed on April 6th, right?
Yes.
Okay. So the first question, comment on the knocking tendency, increase or decrease in SI engines with the following changes. First part of that question is an increase in coolant temperature from 30 degree to 80 degrees Celsius. Second part of the question is a wedge-shaped combustion chamber with a spark plug located at the center of the effective combustion space. Justify your comment with a valid reason. So what is asked in this question is comment on the knocking tendency in SI engine. So it's an SI engine, you know what is the mechanism behind knocking combustion. You have to recollect the mechanism behind knocking combustion in SI engine. And you have to comment on whether an increase in coolant temperature from 30 degree to 80 degree, whether it will increase the knocking tendency or decrease the knocking tendency. First, you need to answer whether it will increase or decrease. Second, you have to justify why it increase or why it decrease. So you need to, in SI engine, knocking happens due to self-ignition of end gas. So when you do this change, you need to analyze in terms of what will happen to the end gas temperature. Suppose if you increase the engine coolant temperature from 30 degree to 80 degree, you have to relate it with end gas temperature. Any increase in coolant temperature, whether it will increase the end gas temperature or not. If it increase end gas temperature, knocking tendency is going to increase. If it decrease end gas temperature, knocking tendency is going to decrease. Did you get what I am saying?
Yes, sir. Yes, sir.
So your answer increase or decrease with this change is based on whether this change will increase the end gas temperature or decrease the end gas temperature. As simple as that. And whatever reason you are providing, increase or decrease, you have to justify why it increase or why it decrease. Okay. Second part is wedge-shaped combustion chamber. You have different combustion chamber we have discussed. One of the chamber design we discussed is wedge shape, and in this case, spark plug is located at the center of the effective combustion space. So you have to think from the perspective of with this kind of combustion chamber design, whether flame travel distance and distance will be reduced, whether the time for flame travel is reduced or not. Okay, also think about what will happen to the end gas temperature. Okay, like I have said for the previous case. So when you have lower end gas temperature, when the flame reaches the end gas quickly with a shorter time interval with a lower distance, then you can expect that the knocking tendency is decreasing. Otherwise, the knocking tendency is going to increase. So with this combustion chamber shape, you have to think all those aspects. What will happen to the end gas temperature? Whether the flame will reach the end gas quickly or not. Okay, that is the distance. And second point is whether there is appreciable turbulence with this design so that the flame travel time is reduced. So you have to think these three aspects: flame travel time, distance, and gas temperature. Clear?
Clear, sir.
The second question is about arrange the following SI engine combustion chamber in the increasing order of knock producing tendency. So you have been given 4 different types of combustion chamber. You know, these 4 types of combustion chambers are based on valve location, intake and exhaust valve location. We have already discussed about that. So you have to arrange these 4 combustion chamber in the increasing order of knock producing tendency, meaning the one that produces highest knock, one that has a highest knock tendency should come at the end. The one that has a least knock producing tendency should come in the beginning. So you are arranging this 4 chamber in the increasing order of knock producing tendency. First, you need to make the arrangement, and after making the arrangement, you have to justify your arrangement with valid reasons. Clear? So it's time up. I stop here. I will continue this in the next class. If you have any questions, you can ask now.
Professor, sir, you have told one thing that the sol value and squish value are interlinked, right, sir?
Squish and swirl, what is the question on that?
Interlinked, it is interlinked, right? If I'm not wrong.
Yes.
If the squish value is high, then sol value will also will be high. If the squish value is low, then sol value also will low.
Yes.
But my point is that, sir, if the this combustion chamber is designed in such a way that after the entering of gases gains the radial component of velocity of the gas, will that not be independent of the value of a squish in that way? Like what I mean to say over here is I can have a lower squish value, but still I can produce high sol basis the what I mean to say the angular momentum of the charge if I am able to impart in the incoming like charge in that.
No, actually you are not generating any energy here, right? So when you are basically through piston shape, you are converting one motion into another motion, radial motion into circular motion. It's just a change of motion, right? In terms of directional change, but energy levels of the fluid, you are not generating any energy here.
Okay.
You are not generating any energy. Whatever the fluid, whatever energy the fluid has, right? It is going to continue with the same energy. Only there is a directional change. From a radial motion, it gets converted to circular motion based on the shape of the piston. One thing that can happen is energy level may go down based on how you shape the piston. Suppose if the squeeze, from the squeeze you are converting to swirl, if the radial motion happens and if the charge goes and hit the ball, there may be some energy loss because of the impingement of the charge on the piston surface. So you may have a loss of some energy, but that can be minimized with appropriate piston bowl design. Okay, you can minimize it, but what I mean to convey here is whatever energy the fluid has, you are not adding any new energy or enhancing energy. What is happening here when you change from squish to swirl motion, it's a directional change in the fluid motion. Energy level may drop to some extent due to impingement, as I said.
Okay, sir. Thank
But
you.
it all depends on how you shape the piston. You can minimize that energy loss.
Understood, sir. Thank you so much.
Okay. Okay.
Sir, am I audible?
Yeah, audible.
Just one question on the assignment.
Yeah, go ahead.
So there was a question on the range comparison between a diesel engine and SI engine in considering the same efficiency between them, right?
The assignment.
Yes, sir. Yes, sir. Assignment 1 question, and you had asked us to comment on the final answer.
Yes.
I think many of us actually couldn't write the proper comment, and that's where maybe over there. Can we
Okay,
just
the
know
comment,
what is the expected?
Yeah, the expected comment here is you need to say whether the mileage is higher or lower. Okay, you have to conclude. You have to conclude finally based on differences of the volumetric energy content for diesel and gasoline with similar engine efficiency. Okay, which engine will give higher mileage, diesel or gasoline vehicle? That conclusion should be there, and that conclusion is based on the difference in the volumetric energy content. You cannot make an absolute comparison here. It's a relative comparison. That's why it is expressed in percentage. Why? Because I asked you to consider diesel as a reference. So it will come in the denominator. Difference in the volumetric energy content of the two fuel will come in the numerator. So you are expressing it in percentage, right? Compared to diesel vehicle, gasoline powered vehicle, whether the mileage is increased or decreased. If you get a negative value, it is a decrease in mileage. Positive value, increase in mileage, and it depends on the value of the volumetric energy content of the two fuel.
Understood, sir. I think we were missing that statement alone. Yeah, got it, sir.
Yeah. So the question itself, comment on the mileage, right? So finally,
Yeah, sir. Understood.
Comment on the mileage in terms of whether it will be higher or lower for one vehicle compared to other vehicle. You can also say other way. For example, you can say that diesel vehicle produces more mileage. So in this case, it is negative value if you consider gasoline. So you can say that gasoline provides less mileage, or in other words, diesel provides higher mileage.
Clear, sir. Clear. Thank you.
Okay, fine. So I will conclude here. I will see you tomorrow at 6 o'clock. Thank you.
Thank you, sir.
Thank you, sir.
Thank you, sir.